Okay, we have our first exam on Friday. It'll be in class, and what I'd like to try to do is I'd like to try to start at 9:35 and go till 10:35, so 5 minutes early and 5 minutes late. So you have an extra 10 minutes on the exam, okay? So try to come a little bit, at least a little bit before 9:35, and we'll hand out, and you can start working at 9:35, and then we'll let you work till 10:35. I will post a review sheet. It's an outline, and anyway, review materials, all the kind of resources for reviewing for the test. I'll post those today on Blackboard. You've got a web work due Wednesday. There'll be another web work like last week. We'll add a second web work, so you have 2 web works due Wednesday. The new one will be on the stuff that we do today. The material that we cover today and Wednesday is on the exam. Okay. We don't start new stuff on Wednesday. We'll just continue what we were doing today. So it won't be just a whole brand new topic, but whatever we do Monday and Wednesday is fair game for the exam. We just made it, okay, in time for the exam. Any questions about that? And then this is I'll post along with the review materials, I'll post this with the blank version, so you can print it out and practice. And then also you have this already. So like I said in the front cover, it'll be like this with all the left sides or the right sides and the equal sides blank. You can just take 30 seconds or 45 seconds before you start and fill this in, and then you'll have it for the exam, and I'll give you a bonus point for doing that if you fill in those correctly. Any questions about the exam? You can email me. But we'll start Friday at 9:35. Okay. So new topic of conversation here. Maybe. There we go. Okay, so we want to start talking about something today called improper integrals. So for those of you who this has gotten a little too mechanical and too just pushing symbols around for a while, you're going to be happier back with this. This is a much more conceptual topic. Improper integrals. So consider a rate of change function that is always positive. Okay, for example, a population that grows by about 2,000 people per year. What is the long-term result to the quantity, in this case population? What will happen if the population has this rate indefinitely? So we have a rate of change of population growing at 2,000 people per year. What will happen to that population in the long term? What will happen? Okay, so you should be thinking it's just going to get bigger and bigger and never stop getting bigger, right? So every year, population's growing by 2,000 people. So it's just the population's just going to get huge, as big as you want, as long as you wait enough time. Because every year you add 2,000 people. Okay, so what is this a graph of? So relative to this context, what kind of graph is that? That's the rate of change graph, right? It's showing that no matter at what time it is, it's the population's growing 2,000 people per year. And so what will the graph of the population look like? Just draw it with your finger. What will it look like? Up and up and up, right? Up and up indefinitely. Okay? Okay, so let's take a look at this then. Let's take a look at this integral. Okay. Do I have Okay, so let's take a look. Say I have a rate of change like this. This is my rate of change function. And consider from x equals 1 to infinity. Again, so I've got a rate of 1 over x cubed. And I'm going to start accumulating at whatever x equals 1 is, and then just accumulate. So by saying from x equals 1 to infinity, I'm just saying just keep accumulating indefinitely, never stop. What will the long-term result be? Well, 1 over x cubed is always positive, right? It's always positive. So I got a positive rate of change, and I'm just going to keep accumulating indefinitely at this rate of 1 over x cubed, which is always positive. So what will the long-term result be? What will the long-term result be? Okay, well, we just saw if I had a positive rate of change of 2,000, and we just let time go indefinitely, it's just going to keep getting bigger and bigger. This is also a positive rate, right? It means the accumulation will always be increasing, right? This positive rate, accumulation will always be increasing. So what's going to happen? What's going to happen? Well, let's find out. Let's do the math and find out what's going to happen, okay? So we would consider what? The net change starting at 1 to infinity at this rate. Remember we worked on that hard in the first week? This would be our notation to represent the net change in whatever quantity that has a rate of 1 over x cubed as we accumulate starting at 1 indefinitely to infinity. So let's do the math on this. Let's do the math on this. So we might think, okay, it's a positive rate of change. Positive rate of change means always increasing quantity. And so we just keep increasing forever, like the previous example. Will the amount just grow indefinitely? All right, so we can't plug infinity into things, okay? Infinity is not a particular value. We can't plug it in, so we need a limit. So we're going to do the limit as and then we're going to do 1 to a. So now we can evaluate that integral and then evaluate the limit, okay? So my experience is lots of students have this mindset of plugging infinity in to solve, plugging infinity in, okay? We don't want to think about it that way. So let's go from 1 to a, some finite number. Let's get that net change from 1 to a, and then let's take a look at what happens as a gets really, really big, or evaluate the limit. Okay, so easy antiderivative, right? That's x to the minus 3, so it's going to be x to the minus 2, right? Raised power. We die for ones like this now, right? And then we need a negative 1/2. And then we're going to evaluate that from 1 to a. So let's switch this back to a fraction. So it's going to be negative 1 over 2. So that's, what is that? Negative 1 over 2x squared, right? That is. Okay, so we have the limit as a goes to infinity. Plugging in a, negative 1 over 2a squared. And then it would be minus a minus, so plus 1 over 2 times 1 squared. Check my math. Did I make any mistakes here? Look good? Okay, so we need a fact now. A fact about limits here. A fact about limits is an important fact. We'll see this later today too. We're going to need it. So fact is that the limit as x goes to infinity of 1 over x to the p equals 0 as long as what do we need p to be in order for this thing to go to 0? So this is all this has to do is get bigger, right? All this has to do is get bigger. So all we need p to be is greater than 0. As long as p is greater than 0, then that will just increase. Even if it's x to the point 1. X to the point 1 just keeps getting larger and larger, and that's all we need in order for this thing to go to 0. So if p is greater than 0. So hold on, that's an important limit. We'll see it'll come back. several times. So as long as p is positive, it can be any positive power of x in the denominator. That as x gets big, that thing will go to 0. Okay, so we're going to use that here. So as a gets really, really big, what does this do? 0, because 2 is greater than 0. See that? Because that 2 is positive, greater than 0, that will go to 0. Leaving this. Answer? 1/2. So what does that 1/2 mean? That 1/2 is the net change in the quantity whose rate of change is 1 over x cubed as we accumulate that quantity from 1 indefinitely. And look, we get a positive number, in fact, a not very big one, 1/2. So what's going on? I thought if it has a positive rate of change, it will always increase. And if it increases forever, the quantity will grow indefinitely. Okay. Yeah, so the way that this, yes, this is positive and increasing, this rate. But what is this rate doing as x gets big? Back to this. It gets exceedingly small, right? So as x gets large, this rate virtually vanishes for large x, right? It's so small. So it gets so small that if you accumulate at this rate, even to infinity, you still end up with a finite amount. So the amount doesn't go up and up and up like that, like the population example. It goes up, but then it levels off because that rate is getting so small, so close to 0. Does this make sense? Okay. So let's try. Well, let's look at that. Okay, so here is, I'm showing the rate, that rate function is 1 over x cubed. And so I'm going to turn on the accumulation function. The accumulation function will keep track of the total, or the net accumulation up to the value of x. I'll make it blue. And so if we integrated from 1 to 6, the total net change would be this y value. If we okay, so now I'm going to zoom out on the x-axis so we can see what's happening for large x. So now, if we accumulate from 1 to 120, the net accumulation will be very, very close to 1/2. And so you see this is just totally leveling off. And why is that? Because that rate function heads to 0 and becomes so small that after a certain x, where x is so large, that rate function isn't really adding any accumulation. So small that it's negligible, and this thing levels off. Unlike the population example, which just kept growing and growing and growing, because it was at 2,000 people per year. Okay, so let's try 1 over x instead. So let's try a different one here. What about 1 over x? So now let our rate function be 1 over x. And we'll just say from 1 to infinity again. Okay, is it always positive? Does it go to 0 like 1 over x cubed? Does that get small? Does that rate function get small? So for a large value of x? Yeah, okay. So for a real large value of x, that's going to get small, and so we expect the same kind of thing to happen, right? So this rate will virtually get so small that if we accumulate on, it's going to level off, right? But so will it level off at a higher value or at a lower value compared to 1 over x cubed? Higher, because it's 1 over x is not going to get to 0 as fast. So it's gonna stay higher, and we're gonna have a higher rate. It's always going to be a higher rate than 1 over x cubed. So we might expect it to level off, but just at a higher value than 1/2. Let's do it. Here we go. Let's do the math. So it's limit as no limit yet. So let's write out the improper integral. So the definition of an improper integral is integrals that involve infinity, some way, somehow. There's different kinds. One way is that one of your limits of integration is infinity or negative infinity. That's improper. So if it involves infinity somewhere in the mix, it's called an improper integral. So the types we're looking at today are the ones that just have infinity or negative infinity as a limit of integration. Okay, so do 1 over x. And we're going to, so remember, we don't plug in infinity. We change it to a limit. So say a infinity, 1 to a. And then evaluate that net change to this finite a, and then we'll take the limit later. Antiderivative. Natural log, you should be thinking. Lots of practice with those. Now, we could put the absolute value on, so let's do that for the first step. But notice where we're evaluating from 1 to a, which is always positive. So we don't, in this case, we could just take the absolute value off and not worry about it. So we're going to have natural log of a minus natural log of 1. Now our fact doesn't apply this time when doing this. No, this is 0. Right? Natural log of 1 is 0. So we need to know about natural log. Our fact that I told you before doesn't apply because it's not a 1 over x to the something. It's ln. So we need to know about the ln. So as your independent variable gets very, very large, what does natural log do? Do you know what that graph looks like? It kind of looks like this. And so the question is, does it level off or does it keep getting bigger and bigger? Yeah, this gets bigger and bigger. It does not level off. So what is this limit? Yeah. What happened? So I thought this rate was going to 0, right? This rate was going to go just like 1 over x cubed goes to 0, just a little bit, it stays high. It's a higher rate, but it still goes to 0. And so the rate will become negligible after some point, and so that quantity should level off, right? What happened? Did we do the math wrong? Let's look at the graphs. Let's look at the graphs of this and compare the graphs to 1 over x cubed. All right, so here is purple. There's 1 over x. Like we said, it's a rate. It'll get very, very small eventually, but it's always a higher rate than 1 over x cubed. Okay, so now let's look at its corresponding. Let's reset the graph here. So whereas the quantity associated with the rate 1 over x cubed levels off at 1/2, the quantity associated with 1 over x is essentially the natural log function, which just keeps getting bigger and bigger. Now that looks like it will level off, but it doesn't. It still gets bigger and larger and larger and larger. Why, right? So why? So we've got kind of conflicting things here. What is going on? Why does the rate functions both go to 0? One of them, its quantity levels off. The other, it will just grow indefinitely large. Any thoughts? So that's kind of the best picture of it. Well, what's the difference between 1 over x cubed and 1 over x in terms of those rates? What do we say about 1 over x? It's a higher rate, right? It's a higher rate. In fact, here we have a situation where, yes, that rate does go to 0, but it's the fact that it's higher to a certain extent, higher, to a certain degree, greater than 1 over x cubed, means that even though it goes to 0, the accumulation of the quantity will still get large in the long run. It will not level off. So, really important concept here. The fact that a rate function goes to 0 would be required or necessary for your accumulation to level off, but it's not enough. It's not sufficient. You see an example where we have an example where, yes, the rate goes to 0, but that quantity is not flying off to infinity. So it's about what? It's about the rate at which the rate gets to 0. How does 1 over x cubed get to 0? How does it do that? Think about x increasing. How does 1 over x cubed get to 0? Rapidly, right? Quickly. It's getting, look how close to 0 it is already at 6 and 7. On this scale, it's almost negligible. Okay? But 1 over x, it's going to 0, but it's going there a lot more slowly. The rate of convergence to 0 is much slower, meaning that we have just a higher rate, and it's high enough to the extent that over time it doesn't get there fast enough, and so the quantity gets large. Okay, so this is what we call, this situation is what we call convergent, or the indefinite integral converges, 1 over converges to 1/2, or the net change over the long run is essentially 1/2. And then this one up here we call divergent. Anytime, divergent is any case where it's not convergent. So that could mean that it just wiggles, never hones in on a particular value, or it gets really big or small. So divergent is anything that's not convergent. Any situation that's not convergent. Where convergent means it's honing in on one particular value. Gets closer and closer to one particular value. That's convergent. It's honing in. This one's honing in on 1/2. And so this integral that we did diverges. 1 over x. We say that diverges. Meaning it's going to get either really, really big, just unlimited, or really, really big negative, or it's going to just keep fluctuating and never hone in on one particular value. That's what convergent is. Hones in, gets infinitely close to one particular value. That's the only way something can converge. Divergent is anything else. Okay, so where's the breaking point, right? So we can think of all kinds of rate functions in between, right? So where's the breaking point? What is fast enough in this 1 over x to the t situation? What is fast enough for it to converge? What's the breaking point? If you went a little bit slower than that, it would diverge. So we can do the math and find out. So somewhere in here, is the breaking point. Maybe it's the last possible one that diverges, and then any rate that falls below that will have a convergent quantity. What is that? So we can do the math to find this out. So what we want to do is, so questions on these two examples or the ideas of convergent or divergent improper integrals. All right. So let's do it again. Do that same example one more time. But now we're going to say integral from And it doesn't matter what we start at, right? So I could start at 100, I could start at 0.5. It's going to give us the same result, right? The long run is what matters. So we'll just, for ease sake, we'll just keep starting at 1 here. And we'll say 1 over x to the p. And we're asking for what p? Does the integral I should say p's. So for what values of p does the integral converge or diverge? What's the breaking point, right? So we know 1 over x cubed, that gets to 0 fast enough for it to converge. 1 over x to the 1, not fast enough. Too slow. It gets to 0, but it still gets there too slow for it to converge. So we'll do it generically for p and figure out what p is going to give us a finite value. For what values of p can we get a finite value for this? We're going to do it one more time. So limit as x goes to a, 1 over a, 1 over x to the p, dx. So how are we going to do this? It's going to be x to the, so this is x to the negative p. So it would be x to the negative p, what? Plus 1, right? That's how you do antiderivative, power rule. You're going to add 1, and then we're going to have 1 over negative p plus 1, right? And that's going to be, shoot, I forgot the limit. That's an easy trap to fall into. You've got to keep that limit notation until you evaluate the limit. So let's get this looking like a fraction. So I think these limits are easier to evaluate as a fraction without negative exponents. So okay, so I'm going to do limit as x approaches a of. So 1 over negative p plus 1 times, we do 1 over x to the p minus 1. Would you agree with that? Right? So opposite exponent when you move it either to the denominator or up to the numerator. So I had negative p plus 1 will be p minus 1 in the denominator. This is a going to infinity, right? Are you thinking that? Not x going to a going to infinity. Don't hesitate to speak up if you're not sure. I was very focused on the antiderivative and all that stuff, and so this is right now, consistent with what we did before. Okay, so now we're ready to evaluate it at the limits and subtract, right? Fundamental theorem allows us to calculate a net change as final minus initial, right? Final value of the quantity minus initial value of the quantity. So we're going to have a 1 over negative p plus 1 times 1 over x to the a minus 1 minus 1 over x to the 0, is that right? Which is just 1. So what are we asking? We're asking, when does this limit, when is it a finite value, or when does it whirl off to infinity? Well, it all comes down to this right here. The limit is a goes to infinity of that thing right there. So I'm just going to extract out just that part. So we're interested in that right there. Yeah, probably. Thank you. right, because it's, we put, yeah, that, we're putting a in for x, right? Okay, don't let the TA beat you to it. If you're thinking this, speak up. Okay. Right, we're evaluating this for x equals a and x equals 1. All right, so now we got this right here. So what do we say? This is where our fact comes back in, right? Our fact. When does this thing go to 0? When? So using the fact. Okay, but what was p before? P was this whole exponent, right? This whole exponent has to be? No, the whole exponent has to be? The whole exponent. So the fact said that the exponent has to be, you're finishing the problem. Yeah. So for it to go to 0, this has to be greater than 0, right? The exponent has to be greater than 0. So that's what the fact said. When that exponent is greater than 0, that thing goes to 0, and that therefore implies that p has to be, now, greater than 1. So going back to this, looking back at this. So when does this, for what values of p does this converge? Converges when? P is greater than 1. So notice, just the limit of that will converge to 0 when p is greater than 0. If you're just taking the limit of that function. But now we're doing the net change of that function as a rate function. Now that p has to be greater than 1 for that net change to converge. Okay, so make sure you see the distinction between the fact. The fact has to do with just a function that approaches 0. As long as that thing is positive, that function will get small. But for the net change to converge, we need p to be greater than 1. So let's go back to the picture. Can I erase this? Okay, so what was the breaking point? Well, this function was the breaking point. This was our 1 over x. That turned out to be the breaking point. As long as this is greater than 1, so it could be 1 over x to the 1.001. Then that p is greater than 1, like we just found. This rate will be just, let's graph that. 1 equals 1 over x. All right, here's 1 over x to the 1.1, the green one. There's 1 over x to the 1.1. Because that is greater than 1, that green one, that will get to 0 quickly enough for this, for your quantity, for your net change to level off in the long run. But starting at 1 over x, and all rates that are greater than that will not converge. They will get large. So 1 over x is the cutoff, and 1 over x has a divergent net change, and anything less than that, 1 over x to the 1.001, like the green one, will converge. That's the cutoff. All right, but that's a very specific rate function, right? So 1 over x to the p . That's a very, very narrow, that's a family of functions, and that's very narrow. There's lots and lots of more situations we can look at rather than 1 over x to the p. So this is not the, 1 over x to the p is not the total of all improper integrals. This is a narrow class of functions. So that rule that we just proved only works for this specific type of rate function. So we need to look at some others too. So, and then when we look at others, how do we know if they converge or diverge? We just have to do the math. We just have to do the math. So, for instance, converge or diverge? Converge, because 10 is greater than 1. Okay? Well, so here's something. Here's an improper integral. Converge or diverge? We don't know. Why? It doesn't match 1 over x to the p. We can't use that conclusion of p being greater than 1 or not if it doesn't follow, if it's not the type 1 over x to the p. If it's anything else, then what we do is we evaluate the integral, and if that integral blows up, then that's a divergent integral. And if that integral converges onto a finite value, then it's convergent. So beyond 1 over x to the p, we have to do the math every time. We have to evaluate the integral. So we're going to do this one. So let's graph that first and see what that looks, this rate function first, and see what it looks like. Okay, so, and I was, integrating from -1 to infinity. So let's zoom out and see -infinity to 1. Okay, so what are we talking about here? So now, it's kind of like we're starting at -infinity, and we're going to accumulate all the way from -infinity to 1. So actually, let's just change it up here so we just do something different than 1. It doesn't have to be 1 every time. So let's do it to -2. How about that? All right, so we're going to consider r of x. This is r of x. And you gotta just have to imagine that we're gonna start at -infinity and accumulate to -2. I know that's a little strange, but the idea is if you accumulated at the rate of this purple curve between -infinity and 2, if you were able to do all that accumulation, would you get a finite value or would it be infinite? And if it were infinite, it'd be negative, right? Because this is all negative right here. So will our net accumulation blow up to -infinity, or will this actually converge on some negative value, right? So how do we find out? We got to do the math. We got to do the math. Okay. So we're gonna let's switch my room here. So we're gonna here we go. We're gonna go -2 or -infinity to -2. The rate of 3x e to the 1/2 x dx, and we know we have to do the limit, and just because we can, we'll do b. There's nothing special about a versus b. So here's what we can do. We can evaluate b to +infinity. It doesn't matter. So we can. And this is something that will be helpful, so I'll just do it this time. But you could evaluate b to -infinity and do b to -2, or you could evaluate b to infinity, and then this would be negative b to negative 2. So same thing. So letting b get very large positive and then evaluating from negative b to negative 2. Sometimes you'll need to do that, so we'll do that here. In this case, it didn't matter. We could do it either way. So now we're ready to evaluate this antiderivative. And so now we look at this, 3x e to the 1/2 x, and we say, oh, I'm really, really smart at all these antiderivatives because it's a harder one. I know what to do. And the first thing I ask is it undoing the chain rule? Is it undoing the chain rule? Some are saying yes. Is it undoing the chain rule? No. How would it need to be different for it to be undoing the chain rule? Yep, good, last you saw it. If this was 1/2 x squared, it'd be undoing the chain rule. But it's not what it is, right? If it's e to the 1/2 x squared, we could undo the chain rule, but we can't. So now we got 3x e to the 1/2 x. Got to reach into our toolbox for something else. And we notice that this is a common form for, you should notice a common form for undoing the product rule, right? What are the common forms? Something like this, x to a power times the e function, or x to a power times sine or cosine. These are the common forms. Or forms involving natural log often are undoing the product rule. If it's not undoing the chain rule, right? Always look for undoing the chain rule. But if it has natural log in it, it's often undoing the product rule. Also, our inverse trig functions are common forms for this. So this is a perfect setup for undoing the chain rule. Here we go. So we got f and g prime, and f prime and g. And what should we set f equal to? 3x, good. Because for this type, we know we want to reduce that power of x, and that's what the derivative does. So our derivative gives us 3. And then we got e to the 1/2 x, antiderivative, e to the 1/2 x times 2, right? And you need a factor of 2. So when you take the derivative of it, the chain rule by the chain rule, you get the 1/2 times the 2 goes away for g prime. Okay, ready to set it up. So what do we got? So we got to maintain this limit as b goes to infinity. And we got what? F times g, 3x times 2e to the 1/2 x minus the other integral, right? The other integral is 6e to the 1/2 x. Check my math, guys. I'm making mistakes today, so. Let's not dig a hole for ourselves. How did I do? Are we good? Agree with that? Okay, and we know we're going to evaluate that integral from negative b to negative 2. We'll also evaluate that, that's not dx, what am I doing? One of those days. This is not an antiderivative, right? This is ready to go. So we're going to evaluate this from a negative b to negative 2, and then we're going to find this antiderivative and evaluate that from negative b to negative 2. Okay. So rewrite that. So 6x e to the 1/2 x. And we know that's going to be from negative b to negative 2. And then minus antiderivative e to the 1/2 x. I have 6. I also need another multiple of 2, right? So 12. And that's going to be from negative 6 to negative 2. Could have just written that once outside the bracket. Doesn't matter. Okay, I'm going to stop and let you catch the likelihood of a mistake on my part. That's what is that? That's 1/2 there. Sorry, can't read that. Are we good? Question? Yeah. What's that? -6. B, it's a B. This over here, this is B. So you can look at this right here. It's just a bad B. These are B's. Are we good? Yeah. Another 2. What's the derivative of e to the 1/2 x? What's the derivative of e to the 1/2 x? Derivative is 1/2 e to the 1/2 x. So if I want my antiderivative to be 1 e to the 1/2 x, I'm going to have to multiply by 2. So I had -6, so it's going to be -12 now. Is it right? Okay. So keep going. So now we're going to start plugging things in. -12 e to the -1 minus 6 times -b e to the -1/2 b. And then plugging in -2, I'm going to get -12 e to the -1. And then this is going to be minus, this is going to be plus 12 e to the -b over 2. Okay, check my math. Is that right? Does it look right so far? Looks okay? All right, so as b gets very, very big negative, this is just itself. This doesn't care what b does, right? There's nothing to do with b. So this is -12 over e. All right, what about this? As b gets very, very large, so we're going to write another step here. A little more to do here. So this would be plus, I'll write this as plus 6b over e to the 1/2 b. And then minus another 12 over e. And then plus 12 over e to the b over 2. All right, now we're ready. Okay, let's start with this one. So this is just going to be itself. These have nothing to do with b, so we're going to get -12 over e and -12 over e. That's good. All right, what about this? The limit as b gets very, very big here. Very small, right? We get a huge denominator, 0. Now what about this? As b gets big, what do we get? Infinity over infinity. How do we evaluate a limit if that's undeterminate? That could go to infinity, that could go to a constant, that could be 0. How do we evaluate a limit where we have initially have infinity over infinity? L'Hopital's rule, right? So we have to use L'Hopital's rule on that, which says that that limit is the same as the limit of the ratio of the derivatives. So I can take the derivative, so it's not the quotient rule, it's truly the derivative of the top divided by the derivative of the bottom. That limit will have the same limit as this. So what is that? 6 over 1/2 e to the 1/2 b. And what's that? So now as b gets really, really big, just like this one now, that goes to 0. Therefore, it's the same as this one. So this one goes to 0. Conclusion? The whole thing equals -24 over e. So our original net change, if this is the rate function from negative infinity to -2, we were to accumulate over that span at that rate of change, we we would get a finite value, negative 24 over e. So that's convergent. That's a convergent integral.